what is the vibrational energy separation? Oh, you know it. Let me erase something for you. Let's say this is the potential energy curve. If I want to draw the energy for the harmonic oscillator, if you represent it by the vibrational quantum number, isn't this E sub 0 sits in the potential well? And then you have high energy when quantum state equal to 1, so that your energy is a 1. Yes? Okay, then of course I will have E equal to E sub 2. Alright, so you have energy levels or state for the vibrational oscillator. What is the energy separation? It's a fancy word asking you what is the spacing. Right, because for harmonic oscillator, we have an energy expression, we know the spacing. Diatomic molecule, we can borrow the same idea, the same energy expression, except now we need to replace with the effective mass, but everything else stands. So if I'm asking you what is the vibration energy separation, it's literally asking you what is the spacing. Now, what is the spacing for harmonic oscillator?
Equal.
Neighboring spacing, so delta E between V plus 1 versus V that equals H bar omega. H bar omega. Very, very good. H bar omega. They equally spaced. The separation between the two neighboring states equals H bar omega. Okay, now we need to apply to this diatonic system. Okay, so we'll take it further. H bar is a constant. Omega is defined as the string constant divided by the mass of the oscillator if it's a full simple harmonic. Now we look at the diatomic molecule. What do we need to do? Yes, we need to replace it by the effective mass. That's the only thing you need to change for the extrapolation. Okay, do we know the K? Yes. That's a bound. So that's your spring constant. That's 516.3. Do we know the effective mass? Right? And you plug in, and you will be able to calculate the energy spacing. Okay. All right. Okay. Very good. All right. And then once you know that, then you can think about the vibration and transition, which we also talked about last Friday. The energy differences between the two states for transit for the system has to match with the incident light or emitted light. That's the same idea. All right. One last question. Yes, now I have diatomic molecules or harmonic oscillators can be different quantum states, depending by it's described specifically by those wave functions with the corresponding energy values. All right, so the state we use the vibrational quantum number V to represent. Now, if I have a transit from one quantum state to the other, it's like me. I'm here. All right, the system. There's a many seeds of a row that I can take. Now, if I want to go from one to the other, Can I jump from the first row? Do I have to do the first row? Only jump to the second row by changing one, do the third and the fourth. Or I can starting from the first row and jump by 3. That is called, in spectroscopy, we call the selection rules. Okay, selection rules determine what kind of transition is allowed. So under the harmonic oscillator model for diatonic molecules, the selection rule only allowed if the quantum number change by plus or minus 1, which means it's only between the neighboring states. Does that make sense to you? Yes, okay. So let's have an example. So if I have the system that at the first excited state, what quantum state is allowed for the system to transit?
Go to 0 or 2.
Either hop it down here. Is that allowed?
Yes.
Or in that case, is it an emission or absorption spectroscopy?
Emission.
Emission, very good. And then what else is allowed? The absorption. Okay, now in this particular slide, we said why the selection rule is really saying that the electric dipole moment of the molecule must change when the atoms are displaced relative to one another. Yes.
So for this selection rule, is it saying that you can only take steps of 1? So like once it transitions from like 1 to 2, then kind of go from 2 to 3, or does that mean that's its full range? Like if it starts at 1, it can only go to 2 to 0.
Delta V, right? Change. I'm using the 1, right? V equal to 1, but just as I'm reading through it now. It suddenly has to have the change in your dipole moment. Under this, and we can have a transition moment. It's in the evaluation of the integral between those two transition states, and that value has to be a non-zero value. In order to satisfy this integral, then what we derive is that you have to have the vibrational selection rule for the homonucleus. When you need to do that, the transition moment will be 0, so all the vibrational transition are forbidden. What that means is that you're not going to be able to see it. It's an infrared inactive. But for the heteronuclear diatomic molecules, then you will be able to see it, but only for the delta V change equals to plus minus 1. Ooh, sounds a little, Alright, so I think my goal is to teach you guys quantum mechanics, but coupled with some spectroscopy, because sometimes quantum mechanics can tell you to develop a particular technique, how we apply to it. In this specific cases, we can borrow the simple harmonic oscillator to diatomic molecules under the same potential energy approximation, and then we can apply to it. But in spectroscopy, how we're going to, there's so many quantum states that is available. So we need to tell you guys what would be the selection rule. The selection rule is the dipole, the electric dipole of the molecule has to change. Now in quantum mechanics, we can evaluate with that transition moment, but I'm not going to go to the lengthy depths of because that will contribute to the quantum mechanics you usually have. So in undergraduate, you're exposed to quantum mechanics. Then you go to the graduate school, you have quantum mechanics again. Then you have a spectroscopy based on the advanced quantum mechanics. Then you have statistic mechanics that's another associated with the quantum mechanics. So I'm not going to dump you guys with all this high-level thing, but I thought it would be good for you to know when you do the infrared spectroscopy. I'm sure some of you guys are going to be exposed to infrared spectroscopy. At least you would know what would be the selection rule. not all the transition states are allowed. You have to have the change in the electric dipole moment. If you have a homonucleus, what is a homonucleus molecule, guys? What is a homo mean?
Same.
Yeah, it's like H2. Do you think H2 has an electric dipole? Huh? So therefore, it's not gonna be infrared. Okay, now why I said it's infrared active or not? Because that transition as a harmonic oscillator, the required energy for absorption to make that transition or emit photons for transition in vibrational motion emits or absorbs the light in the region for the infrared. Are you guys following me okay? So that's why we can use the infrared to probe the vibrational motion. Okay, now for the heteronucleus, then it is allowed. You can see some, but you're only going to see it for the plus minus 1. Okay, so Jordan, you work with Dr. Anderson's group. They're using infrared to do spectroscopy, right? But sometimes you not only see the plus minus 1 change, but they also see the overtone. Have you get? I'm not going to ask about this. You're going to see the delta V equals plus minus 2 transitions. So why that is allowed? This is because under the harmonic oscillator, it is only the neighboring state. But in the real system, the potential energy is the most potential. It's not exactly a harmonic oscillator, so we need to introduce approximation. So therefore, you couldn't see plus minus 2 transition as well. But under the harmonic oscillator, it is only for the delta V equals to plus minus 1. All right, okay, I think that is all I want to talk about it. But under the delta V equals plus minus 1, there's one special transition. It is satisfied for heteronuclear diatomic molecule. It is from 0 to 1. The transition from V equal to 0 to V equal to 1, what do we give a special name to it? We say it is
fundamental transition.
Fundamental transition. So if I say, can you calculate the energy for HCl for the fundamental transition? What does that tell you? That tell you it's jumping from the EV equal to 0 to EV equal to 1. So this transition we name it as the fundamental transition. All right, I think that concludes our discussion for the harmonic oscillator and the diatomic vibration function. Now, what about polyatomic? Because most of the time we expose our polyatomic. All right, now I'm going to have some of you guys read the textbook. But one thing I want to touch bases with you is to, I have a couple minutes, I want to discuss about the degrees of freedom. Did I hear somebody say, ooh? Who said it? So, can you tell me what is degrees of freedom?
I don't know if the degrees of freedom I'm thinking of is the right application for this class or not.
Yeah, so let's say I have water. How many degrees of freedom the water has? 9. Very good.
Yeah,
How do we
that's
calculate that? So you have n atoms in the molecule. Very good. I know you got it. How many atoms in the hydrogen molecule? 3, right? 2 hydrogen, not hydrogen, water molecule. 2 hydrogen, 1 oxygen, so N equal to 3. 3 atoms. Now, each of the atoms, how many degree freedom do we use to describe that? 3. 3n degree of freedom. Now let's say I have HCl. Oh, let's do a big one. How about this methane? How many degree of freedom do I have? Yeah, methane, let's see. Let me think about this. I'm not an organic chemist, but that's no excuse for me not to know how many carbons. One carbon for hydrogen,
It's 5.
5 times 3, 15. Okay, all right. Now, that's total 3n.
Some dimensions that we're in.
Out of that
1, 2 dimensions,
3n,
3.
we're going to describe the motion for the molecule. What kind of motion we are talking about? Translational, right? What else the molecule going to have? Rotational. What else do we have?
Vibration.
Oh yeah, very good. Okay, now as a molecule as a whole, how many degree of freedom we can take to describe the translational motion for the molecule in XYZ? How many? 3. You guys are all okay with that, right? Now for rotational, it can be either 2 or 3. It depends if the molecule is linear or non-linear. Okay, all right. Let me write this really nicely. So this is a total of 3n. So this is if it's a linear molecule or non-linear molecule. Okay, I have total of 3n. I have total of 3n degree of freedom. 3 out of 3 translational, either 2 or 3 is vibrational. So how many remains? Oh, rotational, how many remains for vibrational motion?
Just 1,
3n minus either 5 or 6. Does that make sense to you guys? So if you look at the vibrational modes, in the future, if you look at polyatomic vibrational modes, that has to match with the number right there. 3n minus 12. Either 5 if it's a linear, and minus 6 if it's a non-linear